Okay, so now we're going to do example number 3. This example consists of a two-tank system where there is a tank on the right, where water is flowing from the tank on the right through this crazy Rube Goldberg style piping system into a lower tank. And in the upper tank, there is a sharp entrance, and in the lower tank, it is a sharp exit. This piping system in total has a length of 20 meters, and it consists of 6 90-degree threaded elbows, and the change in the elevation between the top tank that is draining is 2 meters from the level of water in the lower tank here. Okay, and so there is water flowing in these tanks. The volumetric flow rate is 0.002 cubic meters per second. And because it's water, we'll probably need the kinematic viscosity, so I looked that up for you. And it is 1.307 times 10 to the minus 6 meters squared per second. And also the pipe is made of cast iron. Okay, and so we are to find the diameter. Okay, because this Q is the minimum flow rate. So here we're trying to find the smallest diameter pipe, which permits a flow rate that is at least this. You could certainly use larger pipe, but then that gets more expensive. And so we're going to solve this problem. So the solution, again, making the standard assumptions, that is steady flow, incompressible, etc., etc., etc. So solution, again, using the standard assumptions. Again, in your homework, you would actually explicitly list all those assumptions as I've shown in all the other problems. So we're going to use the energy equation here. So that would be P over rho G. Not close that just yet. Plus the kinetic energy bogey factor times the average velocity squared over 2G plus Z at the outlet state or some downstream state minus P over rho G plus the kinetic energy bogey factor times the average velocity squared over 2G plus Z at some inlet state upstream equals any power going into the piping system over divided by m dot G minus any turbine work going out divided by m dot G minus the total head losses. Okay, and so here we need to start picking our states in and out. And so in, again, for this type of system is designed to be upstream. And so that is upstream of this point here. And so we will label this as point 1, which is in. And because that is the downstream direction, it is in the opposite direction of the flow through the piping system. And then we follow the flow through. And for ease, we will pick the outlet state, or state 2, to be here. And the reason that I'm choosing them to be here is at the top, we know both the pressure and the velocity squared. Because again, we're going to assume a large tank, so the velocity squared at the top of each of these two tanks is essentially 0. And the pressure is atmospheric, so those two terms cancel. So we can say that U AVG1 squared is small, and U AVG2 squared is small, because we're assuming the A tank is large. Okay, so that means these two terms go away. We don't care about them. Also, we know that P in equals P out equals P ATM. Well, then that means that this term here is identical to that term here. So basically, these two terms here perfectly cancel out, and we don't need them. And I'm going to scroll back up to the diagram. We need to pick a datum, and there's a convenient datum here. So I'll choose this to be the datum. Okay. So Z2, which is the outlet, is at the datum, so that's 0 meters, and Z1, which is the inlet state, that tank height is at 2 meters. Okay, so we can cross out Z2 for the outlet. That goes away, and this is 2 meters. And we don't have any pumping work in, and we don't have any turbine work out. So what we are left with is, this implies that minus Z in equals minus the total head loss, or Z1 equals the total, not HLT, HTL, the total head loss. Okay, so this is our energy equation here. Now we know Z1, which again is 2 meters. Now we need to find the total head loss. And the total head loss equals the head loss due to major losses due to pipe wall friction through the pipe system, plus the head loss due to plus the head due to minor losses through elbows and other components in the tank. Okay, and so this term here is defined by the sum of the Darcy friction factor times L over D times U average squared in the pipe that it's currently in. And the minor losses are defined as the sum of a loss coefficient, which we need to get from tables, times the average velocity squared over 2g. Okay, and so now for both of these we need the average velocity squared, so we might as well find the average velocity. Okay, so we'll assume, we'll just stick in what we know, that the average velocity equals q over the cross-sectional area, which is pi over 4 d squared, because it's a circular pipe. And unfortunately here we don't know d, but we do know q, so let's just stick in the numbers that we do know. So this equals 4 over pi, q over d squared, and that equals, if we stick in the numbers, 4 over pi times 0.002 cubic meters per second over the diameter squared, which we don't know yet. And this implies that the average velocity equals 0.00255 cubic meters per second divided by d squared. Okay, so again, we now have if we know the diameter, we can now find the average velocity. Then for F, we are going to need to know the Reynolds number. And so RED equals rho times U averaged times the diameter divided by mu, or if you prefer, you can use U averaged times the diameter divided by the kinematic viscosity nu. Because recall that nu equals a mu over rho. Okay, and so we have a rho divided by mu, which is just 1 over the kinematic viscosity. Okay, and so this equals, just stick in our formula for U average, 2.55 times 10 to the minus 3 cubic meters per second divided by the diameter squared times the diameter divided by the kinematic viscosity, which is 1.307 times 10 to the minus 6 meters squared per second. And this implies that the Reynolds number based on diameter is 1951 meters over the diameter. Okay, and so that's what that is. So now we are prepared to find the major and minor losses. I'll start with the minor losses because those are a bit more straightforward. So the minor losses, which again are due to fluid frictional effects as it gets turned or interacts through some piping components such as a valve or an elbow or an inlet from a tank, something like that. And so the head loss due to the minor head losses is the sum of the loss coefficient for that component, or for each component, times the average velocity squared in that component divided by 2g. And for this, u average squared over 2g is the same for all components. Okay, which means that we can yank that out, and this equals u averaged squared over 2g times the sum of the loss coefficients. So now we need to find the sum of all the loss coefficients for all of our components. And so now we kind of make a bill of materials. And so here we have 6 90-degree threaded elbows. And the KL for them is 1.5 each. And that's from table 8.2. Okay, and we have one sharp entrance. And that KL is equal to 0.5, and again that's table 8.2. And then we have one sharp exit. Okay, and that KL turns out to be 1. Okay, and you can see that if you look at figure 8.15 on the right, and if you look at figure 8.15 on the right, we would have A1 divided by A2 equals 0, because A2 would essentially be infinity for the very large tank. And so if you look at that, that will tell you what KL, that will tell you what to use for that KL, which was 1. Okay? So this equals 6 times 1.5 plus the sharp entrance, which is 0.5, plus the sharp exit, which is 1. And so if you punch in the numbers, this equals 10.5. Okay? And so we can punch in the numbers that we do know, everything except for the diameter. So we have the minor head losses is equal to 0.00255 cubic meters per second over the diameter squared. That quantity squared, this is just U average squared, divided by 2g, so that's 2 times 9.807 meters per second squared, times the sum of all the loss coefficients, because again, they all have the same average velocity squared. And if we punch in the numbers, this turns into 3.481 times 10 to the minus 6 meters to the 5th over diameter to the 4th. Okay. So we've done the minor losses. Now we got to do the major losses. Okay, and for these, we need to know what flow regime we are in, but unfortunately, we don't know the actual Reynolds number. We know it up to a diameter, which we don't know, but we won't know the actual Reynolds number until we know the diameter. So we don't know the flow regime. So you need to assume that the flow is either laminar or turbulent. And so let's look at RED again, just so we can get a fix on it. RED equals 1951 meters over D. And so if we consider how small that flow rate is, 0.002 cubic meters per second, it is unlikely that the diameter of the pipe is going to be on the order of a half meter. It's probably going to be much smaller than that, on the order of maybe a few centimeters. So if the diameter is on the order of a few centimeters, then this Reynolds number is going to be on the order of 10, 20, 30, 40,000, which is going to be far greater than 2,300. So for this particular problem, it is probably safe to assume it's turbulent. So let's assume that it's turbulent. And then we solve the problem, then verify. So if we assume it's turbulent, we can get the friction factor that we need for the major head losses, and then you can solve the problem, get the diameter, and then find the Reynolds number, and make sure that it's in a turbulent flow regime. If not, then we guessed incorrectly, and we need to assume that the flow is laminar and go through it that way. Okay, and so let's just assume it's turbulent. So HTL major, that equals the sum of the Darcy friction factor times L over D for each pipe section times the average velocity squared over 2G. Well, here there's only one, we are only given one section of pipe, even though it's cut up by a bunch of elbows. But they all have the same diameter, and so this equals F L over D times U averaged squared over 2G. Okay. And this L here, we're given the problem statement is 20 meters, because the total length of the piping system is 20 meters. Okay, and so this equals F times 20 meters over D times the average velocity squared over 2G. So 0.00255 meters cubed per second over D squared. That quantity squared over 2 times G, which is 9.807 meters per second squared. Okay, and so this equals F, which we don't know, divided by D to the 5th times 6.63 times 10 to the minus 6 meters to the 6. Okay, so now we need F, or at least a formula for F. Okay, and you have two choices here. You can use the Moody chart and iterate with that, but you don't know the diameter, so you don't know the Reynolds number, and so that becomes a bit of a pain. I find it's easier to use the Colebrook equation. So from the Colebrook equation, or Moody, if you really want to go that route. So we can just simply solve 1 over square root of F equals minus 2 log base 10 of the relative roughness epsilon over D divided by 3.7 plus 2.51 over the Reynolds number based on diameter square root of F. Okay, and so we know RED up to the diameter, and so now we need to find the relative roughness. So just to refresh your memory, RED equals 1951 over D meters. Okay, and epsilon equals 0.00026 meters. That's from table 8.1. And so I'm just going to put an I'm just going to put in the relative roughness divided by 3.7, which would give us this entire term right here. And so epsilon over d divided by 3.7, that equals 0.00026 meters over the pipe diameter divided by 3.7, and that equals 7.027 times 10 to the minus 5 meters divided by the diameter. Okay, or if we punch in the numbers, 1 over square root of f equals minus 2 log base 10 of 7.027 times 10 to the minus 5 meters over the diameter plus 0.001287 meters to the minus 1 times d over square root of f. Okay, and this term here is simply 2.51 over RED square root of f. And I just basically punched in the numbers for RED for that. Okay, and so this here is equation 1. We don't know f and we don't know d. Okay, and also notice that if d has units, if d were to have units of meters, this meter here would cancel out with this meter to the minus 1 here, which would be unitless as it should be, and this meter here would cancel out with this meter here, and so the equation works out if d is in units of meters. So this works if d is in units of meters. And so that's part of why I'm picky with the units, but when we get to actually solving these equations, you can't put the units in the equation solvers. This can be a bit more sticky when you're using the English system, and if you're dealing with feet and inches in the exact same problem, you may have to find in one equation d will have to be in feet, and in the other one you'll have to convert it to 2 inches. But to counteract that, as I've done with all the other problems, I converted everything to feet and then work with that consistent unit system. Okay, so now we know F, we know the head losses in terms of both F and D. So now we just need to stuff those into our energy equation. So now, back to the energy equation. Okay, and use HTL, minor and major, okay? Because we know that. And so that was Z at the inlet state equals the total head loss, or this implies that 2 meters equals equals the major losses, which is F over D to the 5th times 6.63 times 10 to the minus 6 meters to the 6 plus 3.48 1 times 10 to the minus 6 meters to the 5th over D to the 4th. And again, the units work if D is in meters. Again, I'm just picky with this because if you're dealing with a mixed lengths like you do in English system quite often, this equation might want D in terms of inches, and this equation here, it might want D in terms of feet. Or this term here might want D in terms of inches, and this term here might want D in terms of feet. So you just need to be really careful with that with the English system. Okay? So, and I'll call this equation 2. Okay, and so we don't know F or D, so we need to solve 1 and 2 simultaneously. And so just to recap, that was 1 over the square root of f equals minus 2 log base 10 of 7.027 times 10 to the minus of 5 over d. And again, I'm dropping the units where we'll assume d is in meters. Okay, because we've already done the unit cancellations. If we do that, plus 3.481 times 10 to the minus 6 divided by d to the fourth. And so that's equation 1. And for equation 2, we have 2 equals f over d to the fifth times 6.63 times 10 to the minus 6 plus 3.481 times 10 to the minus 6 divided by d to the fourth. And so we essentially have 2 nonlinear equations for 2 unknowns, and we need to solve them. Okay? And so where d is in meters. Okay? And so solve using, again, I'm going to show you. I'm going to show you using Wolfram Alpha, but you could use, but MATLAB or some other tool would be a fine choice for doing this. Okay. And so we'll do this. I'm going to do another live demo with the solver. Odds are I'll probably goof it up. Okay, and so we want to solve those 2 equations in 2 variables. So again, we use the find root command, and now we have 2 equations. And so we put the list of equations in curly brackets, and then we simply type what the equations were. So it's 1 divided by the square root of the friction factor equals minus 2 times log base 10 acting on 7.027 e to the minus 5 divided by the diameter, which I'll just call small d here. Plus 0.001287 times d divided by the square root of f, close bracket for the log, and so that closes our log, so that's our first equation. Then we put in the second equation 2 equals f divided by d raised to the 5 times 6.63 e to the minus 6 plus 3.481 e to the minus 6 divided by d raised to the 4th power. And that's our second equation. And now we have a list of variables. So the list of variables goes in a set of curly brackets. And each variable and their initial guess goes in another set of of curly brackets. So I'll guess, say we are solving for f, and we'll use a starting guess of 0.1. Oops, not a whole bunch of points, just the 1. And we'll use a guess for the d of, say, 1 centimeter, so 0.01. Okay, so that closes the list of variables that we're solving for and the initial conditions. So now hopefully I've entered the equation properly, and we just need to solve. Hey, first shot. Okay, and so here, when on unless you get some sort of error, always check the input interpretation box and make sure that the equations are exactly the equations that you are trying to solve. This can help you find out, because basically this is written in a more human readable manner, and so it's easier to read this than the long single line command above. And so this looks correct, and so we know that the friction factor is 0.03359, and the diameter is 0.04527 meters. Okay? So we do that, and we find that F equals 0.03359, and the diameter equals 0.0453 meters. And so it's not time to rejoice yet. We've not necessarily solved the problem. So we need to check RED to make sure our turbulence assumption is correct. Okay, and so RED equals 1951 meters over D, and that equals 1951 meters over 0.0453 meters, and that implies that RED equals 43,000 roughly, and that's greater than 2300, so that is turbulent. And so our assumption was correct. Okay, and if RED happened to be less than 2300, we would have to redo the analysis with the Darcy friction factor and use the laminar relation for that. Okay, and so we can conclude that the pipe diameter is equal to 45.3 millimeters.